Hi, my name is Brian Caffo, and this is a lecture on multivariable regression in the Coursera class on regression. This class is co-taught by my collaborators Jeff Leake and Roger Pang. So in this class, I'm going to just go through some simulated data and just show you kind of examples of adjustment and what adjustment is accomplishing and what kinds of things can happen. And I'm going to use simulated data so that we can kind of know the truth. Okay, so I'm going to set n of 100, and then let's see. So t here. Let me get that a little bit better. Is a kind of a treatment effect. So that variable looks something like this. This variable right here looks something like zeros repeated n over 2 times and then ones repeated n over 2 times. Okay? And then my x variable is just a series of uniform random variables. I don't know why I did it that way instead of just doing runif n. Here's my intercept, my slope, which I set to be 2, my tau, which is going to be my treatment effect, and then my variance. Okay, so I simulate my outcome. It's my intercept plus my regressor times my slope coefficient plus my treatment effect times the treatment effect parameter plus the epsilon. That part right there is like epsilon. So we're sort of fitting the model. Yi equals beta naught plus beta 1 xi plus beta 2 ti plus epsilon I, where ti is a 0, 1 variable. Okay, and then I'm going to plot it, my x and my y, and then I'm going to add a line where I disregard the treatment, and then I'm going to I'll tell you what these are, or I'll show you. I think this will be clear why I do this in a minute. This is the mean for the treated group, for the untreated group, right? This is the mean of the first n over 2 observations, and this is the mean of the latter n over 2 observations. And then this is the model we fit that's correct, that includes a treatment effect. And then I'm going to plot the fitted lines for the two of those. And then this plot, the first plot right here, actually, I have this type equal n right there, and that just means I didn't actually do the plot. It just created the frame, and then here I actually do the points. And I did it that way, so A, I could have different color points for the treated and the untreated group, and B, I wanted my points plotted last, so they go on top of the line. So, okay. Go through that code. It's in the Slidify notes. Okay, and it looks something like that. Okay, so this is a pretty good example of regression adjustment, or a pretty reasonable example of regression adjustment. So the true lines are parallel, so that the effect of treatment holding x constant is the same. So regardless of what x we look at, that distance is the same. So the real kind of adjusted treatment effect is that one. In this case, it makes sense to talk about a treatment effect. But if we were to disregard treatment and just so this is the effect that we get if we fit the model LM y tilde x plus t. Right, that adjusted treatment effect is that guy right there, that distance right there. But if we disregarded it, I show it right here. Here's the difference in the means if we were to have disregarded x and just done absence of covariate adjustment. And to me, those look about the same. Okay, which is good. Means that it didn't matter whether we regressed on x or not. But let's keep going. Okay, so let's discuss this first, and then we'll keep going. It's going to get harder. So some things to note about this simulation. The X variable is unrelated to group status. It's uncorrelated with group status, right? It was just a bunch of uniform numbers. So the X variable is related to Y, and the intercept depends on group status, right? We had two separate lines. And then, of course, in this case, the group variable is related to Y. And we have a meaningful treatment effect. The group status in Y is constant depending on X. That means the two lines are parallel. Okay, and that's just reiterated in this last point right there. Okay, so now let's look at some harder cases where things are less clear.